Let knowledge flow like a river without any hindrance. Don't make it like a stagnant pool. Examples and behavioral analysis of a beam under different load and support conditions. Part 3. Hello everybody, I'm Peter Strategy with you. Today I am going to explain you how we can calculate bending moment and shear force of a beam under different load and support conditions in Excel. This is part 3. And in this part, you are going to watch for the uniformly varying triangular loads. Before start of the lecture, please like, share and subscribe my channel. Uniformly varying load type. Type 1. Here, in the right hand support, load is maximum. Load type 2, left hand load is maximum on left hand support. Load type 3, here, load is maximum at the center of the beam. Basic data for calculation. First, I am considering load type 1. So, length of the beam and load on left hand support is 0. Load on right hand support is W per meter. Left hand support reaction RA and right hand support reaction RB. Distance of load C from left hand support to L by 3. From right hand support L by 3. Point of contact fracture for load type 1. Definition of point of contact fracture. Point of contact fracture is that point within the length of the beam but shear force changes its side. At this point, stand bending moment for simply supported beam will be maximum. Load diagram for maximum span moment and point of contact fracture. So, point of contact fracture X. And we are considering the load left hand side of the point of contact fracture. The total load will be P1 and it will act at the center of this triangular portion, PG of this triangular portion. And length of P down from point of contact fracture is equal to K1 is the 1/3 A. Calculation of the point of contact fracture for the triangular load type 1. First we have to consider first we have to calculate total load. It is WL by 2. The reaction RA is WL by 2 into L by 3 by L. Actually, this load, total load will be distributed towards the support in the ratio of CG length. So RA is equal to LWL by 6 and reaction RB is equal to WL by 2 into P3 L by L is equal to WL by 3. So this terms of point of contact fracture from left hand side is equal to X. Load on point of contact fracture is equal to WX. Total load on left hand side of the point of contact fracture is P1. Now load intensity, that is change in load or unit length is equal to W by L. Load at X is let's say WX. Then Wx is equal to X into by L. Total load on point of contact fracture P1 is equal to half X into Wx. Is equal to X by W into X into W by L is equal to Wx squared by 2L. 0. P1. Therefore, Wx square by 12 is equal to W into L by 6 or X or point L by root over 3. Now, simply suppose its span moment for load type 1 and load type 2. Maximum simply suppose its moment at the point of contact action is equal to K1 is equal to 1/3 and X is equal to L by 1 by root 3. We know RA is equal to WL by 6 and P1 is equal to W X square by 2L. So, moment of POC is equal to MS. Therefore, MS is equal to RA minus RA into X plus P1 into Q1. Therefore, MS is equal to minus W into L into X divided by 6 plus WX square by 2L into X by 3. So, equal to minus W into L into X divided by 6 plus WX cube by 6L is equal to WX by 6L into X square minus L square. Therefore, MS is equal to W by 6L into L square root of 1/3 into L square by 3 minus L square is equal to minus W square by 6 into square root of 1/3 into 2/3 is equal to minus 1 by 9 square root of 3 into WL square. So, MS is equal to this value. Sample diagram for load type 1. I have nothing to explain. Bending moment diagram for load type 1 will be like that. This is bending moment diagram for load type. The value will be same, the position will change. Moments. Say total load in hatch portion, that's means in this portion is equal to P1. Load in intensity is equal to W by L. There is change in load. Uniformly varying load at C is equal to X distance into W by L. Total load in hatch portion is equal to X into W by L into dx. Dx is a thickness, smaller thickness. ACM at A for point load P is equal to MFA is equal to PAB square by L square. And here A is equal to X, B is equal to L minus A. Therefore, MFA is equal to dx into WH by L into X into L minus X square divided by L square. By differentiating this equation, we have dMFA by dx is equal to dx by dx into WX square by L cube into L cube minus 2LX plus X square is equal to W by L cube into L square X square minus 2LX cube plus X to the power 4. Therefore, dMFA is equal to WL cube into dx into L square into X square minus 2LX cube plus X to the power 4. By integrating this equation, therefore, limit 0 to L, dMFA is equal to L square, WL square by 3 WL square by L cube into integration of x square limit 0 to L minus 2LW by L cube into, once again, the integration of x cube limit 0 to L dx plus WL cube into integration of x to the power 4 limit 0 to L dx. Therefore, integration of dmx is equal to W by 3L into x cube minus 2W by 4L square into x to the power 4 plus W by 5L cube into x to the power 5. Here 0 to L, 0 to L, 0 to L are the limits. Therefore, MSA is equal to WL cube by 3 minus WL to the power 4 by 2L square plus WL to the power 5 by 5L cube is equal to WL square by 3 minus W square by 2 plus W square by 5. MSA is equal to W into L square minus 15 into W into L square plus 6 into W into L square divided by 30 is equal to 1 by 30 WL square. Finally, we have fixed end moment at A, that is left hand support, is equal to MSA is equal to 1 by 30 W L square. Fixed end moment at B for point load P is equal to MSB is equal to P S square B by L square. And here A is equal to X, B is equal to L. Equal to dx into Wx by L into x square into L minus x by L square. By differentiating this equation, we have dmf dx is equal to dx by dx into Wx cube into L minus x divided by L cube is equal to WL cube into L into x cube minus x to the power 4. Therefore, dmf d is equal to WL cube W by L cube into dx into minus x to the power 4. By integrating this equation, once again limit 0 to L, dmf d is equal to W by L cube integration of L into x cube dx minus W by L cube into integration of x to the power 4. Therefore, mf d is equal to W by L 4L cube into L to the power 4 minus W by 5L cube into L to the power 5 is equal to W square by 4 minus W square by 5 is equal to 5W square minus 4W square by 20. Finally, we have fixed end moment at D is equal to MFD is equal to 1 by 20 WL square. Span moment for the fixed end beam MSS. FEM at A is equal to MSA. At B, MFB. FEM fixed end moment at A is equal to MSA and at B, MFB. At POC say moment is equal to MFS and singly supported moment at POC say MS. We know FA is equal to WL square by 30, FB is equal to WL square by 20. MS is equal to minus W square by 9 root over 3 and POC point distance of point of contact flexure from left hand support is equal to L by square root of 3. MFS is equal to MS
plus MFA plus MFB minus MFA by L into X. MFA plus MFB minus MFA into 1 by L into X is equal to WL square by 30 plus WL square by 20 minus WL square by 30 into 1 by L into L by square root of 3 is equal to WL square by 30 plus WL square by 60 into square root of 3 and is equal to 6 into W into L square by 180 into square root of 3 into WL square by 180 is equal to 6 plus square root of 3 into WL square by 180. Therefore, MFS span moment maximum
to minus W square by 9 into square root of 3 plus 6 plus square root square by 180. NFS is equal to minus square root of 3 into W square by 27 plus 6 in 6 plus square root of 3 into W square by 180 is equal to minus 20 into square root of 3 into W square plus 18 into W square plus
to 540. That finally MFS is equal to W square by 540 into 18 minus 17 square root of 3. Bending moment diagram for triangular load type 1 and 2.
we got the bending moment diagram for load type 1 and load type 2. Support reaction for the fixed end beam RA and RB. Total load P is equal to W into L by 2. MP is equal to MP is the moment due to load P is equal to P into L by 3 is equal to W L square by 6. It is anti-clockwise, so it will be positive. Now we know MFA and MFB is equal to MFA minus MFB is equal to W square by 30 minus W square by 20, or MFA minus MFB is equal to minus W square by 60. By equating clockwise and anti-clockwise movement, we have RA into L plus MFB is equal to MFA plus MP. The RA is equal to MFA minus MFB by L plus W square by 6L. Finally, we have support reaction RA is equal to WL by 30 minus WL by 20 plus WL by 6 is equal to 3WL by 20, and the RB is equal to W into L by 2 minus 3WL by 20 is equal to 7WL by 20. Shear force for the fixed end beam DFA and DFB. This is the diagram of shear force for load type 1 and load type 2. Deflection of span of the fixed end beam, say it is Y max. Deflection pattern of the fixed beam for load type 1. arrangement of loads for maximum deflection. Say at existence from left hand side, maximum deflection will occur. Now Wx is equal to x into W by L. Ra is equal to 3 WL by 20. And MFA is equal to WL square by 30. We know that. Now load, total load left hand side of this x is P. P is equal to x by 2 into W x by L is equal to W x square by 2L. MP, that is moment due to P is equal to W x square by 2L into x by 3 is equal to W x cube by 6L. And moment due to reaction Ra is equal to MRx is equal to minus 3W into L into x by 20. Differential equation of moment at any section, Mx is equal to Ei into d2 dy d by Mx is equal to Ei d2 by dx2. Mx is equal to Fa plus Mp plus minus Mrx is equal to W square by 30 plus Wx cube by 6L minus 3WL into x by 20. Or d2 by dx2 is equal to mx by e is equal to wl square by 30 ei plus wx cube divided by 6 eil minus 3wl into x by 20 ei. By integrating this equation, we have d by dx is equal to wl square into x divided by 30 ei plus wx to the power 4 divided by 24 l ei minus 3WL into x square divided by 40 EI plus C1. C1 is the coefficient for differential equation. When x is equal to 0, d by dx is equal to 0 and C1 is equal to 0, therefore equation becomes d by dx is equal to W square into x divided by 30 EI plus Wx to the power 4 divided by 24 LEI minus 3WL x square divided by 40 into EI. By integrating this equation once again, we have y is equal to WL square into x square by 60 EI plus Wx to the power 5 divided by 120 LEI minus 3W Lx cube divided by 120 EI plus C2. Once again, when x is equal to 0, y is equal to 0, therefore C2 is equal to 0. Therefore equation becomes y is equal to 2WL square into x square divided by 120 EI plus xw into x to the power 5 divided by 120 LEI minus 3WLx cube divided by 120 EI. Or y is equal to 1 by 120 EIL into 2 WX cube into x square plus WX to the power 5 minus 3 WL square into x cube. We know when x is equal to L by 2, that is basement, deflection will be maximum. Or y is equal to 1 by 120 EIL into 2WL cube into L square by 4 plus W into L to the power 5 by 32 minus 3WL square into L cube by 8. We have just put the value of x as L by 2 and we are getting this equation. Now y is equal to 1 by 120 EI into 16 W into the power 5 by 32 once again I am multiplying both numerator and denominator by 8, so 60 by 32. And this is same, this is also, and multiplying this is also by 4, by 8. So it will be 12 and it will be 32. So W square by 5, 120 EI, 16 plus 1 minus 12 divided by 32, or Y is equal to WL square by 4 divided 120 EI into 5 by 32, or finally we have maximum deflection of the fixed mid span is equal to Y max is equal to WL to the power 4 divided by 768 EI. Formula for fixed end moment support reaction and deflection for load type 2. It will just reverse and span moment will be close to left hand support. Here the formula FA is equal to 1 by 20 W square W square. MFB is equal to 1 by 30 W square. MFS is equal to same formula W square by 540 into 18 minus 17 square root of 3. Support reaction RA will be 21 into W into L divided by 60. RB is equal to 9 into W into L divided by 60. And Y max, value of Y max will be same. W square by 180 into 1 minus 5 by square root 3 square root of 3. Simply supported beam with triangular load type 3. Number 1, load equal to W per meter at the center, and support it is 0 per meter. Now the total load P is equal to W into L by 2. P1 is equal to half of P, that is W into L by 4. Here RA is equal to RB is equal to P1 is W into L by 4. So if at A and B are VA and VB, then VA is equal to VB is equal to RA is equal to RB is equal to W into L by 4. Span moment is equal to MS. Right. MS is equal to RA into L by 2 plus P1 into L by 6 is equal to minus W into L by 4 into L by 2 plus W into L by 4 into L by 6 is equal to minus 1 by 12 WL. And this is our Theophilus and Renewal diagram of simply supported beam with triangular load type 3. Fixed end beam with triangular load type 3. Distribution of load for fixed end moment. We have to split the beam into 3 equal parts. Its length is L by 3. Total length L. Which is this portion is L by 3, this portion is L by 3, this portion is L by 3. So we have load intensity W1. This is also W1 and this is W. Change in load is equal to W into L by 2. Within the half length of the beam, it is varying from 0 to W. So W into L by 2 is equal to 2W by L. Therefore W1 is equal to Q Q into L by 3 is equal to 2W by 3. P1 is equal to P3 is equal to half into L by 3 into W1 is equal to half into L by 3 into 2W by 3 is equal to WL by 9. P2 is equal to W1 plus W2 plus W1 divided by 3 into L by 3 is equal to 2W1 plus W1 divided by 9 into L. So we get 19 into 4W by 3 plus W into L is equal to 7 WL by 27. This chart shows that this is P1, this is load value WL by 9, distance from distance A is equal to L by 2 by 2L by 9, B is equal to 7L by 9. P2 is equal to 7WL by 27, A is equal to L by 2, and B is equal to L by 2. P3, WL by 9, and distance from left hand support and right hand support are L by 7 by 9 and 2L by 9. We know moment due to a point load P is equal to P into A square by L square for left hand support. Say P1 producing M1 moment at the left hand support, so M1 is equal to WL by 9 load into E, 2L by 9 into 7L by 9 whole square. Ultimately, into 1 by L square is equal to 98 WL square by 6.61. Similarly, M2, this is point load at center, we know it will be 2W L by 27 into L by 8 is equal to 7M square divided by 216. And moment produced with P3 at left hand support is equal to M3 is equal to WL by 9 into 7L by 9E, and this displacement 2L by 9 into whole square into 1 by L square is the 28 WL square divided by 6.61. MFA, total moment, fixed end moment at left hand support is equal to M1 plus M2 plus M3. MF is equal to 98 WL square divided by 6.61 plus 7 WL square by 216 plus 28 WL square divided by 6.61 is equal to WL square into 64053 divided by 1417176, or MF is equal to 98 WL square divided by 651 plus 7.30 into 735 WL square divided by 651 plus 28 WL square divided by 6561 is equal to 98 WL square divided by 6.61 plus 212.625 divided by 6.61 into WL square plus 28 WL square divided by 6.61, or MFA is equal to WL square in divided by 6.61 into 90 plus 212.625 plus 282 is equal to 338.625 divided by 6.61 WL square, or MA is equal to 383.625 divided by 6.61 WL square. Value of the coefficient of the WL square is 0.51612. as per SP16, MFA is equal to 5 by 96 WL square. Value of this coefficient 5 by 96 is equal to 0.052083. We know stand moment for simple supported beam with a triangular load type 3, M is equal to WL square by 12. The maximum 50% of this moment we can transfer to the support. Therefore, maximum ratio of MS is to MFA is equal to 1.5. Therefore, MFA is equal to MS by 150. So, this is WL square divided by 150 into square. So, this is WL square by 18. In fraction, value of 1 by 18 is equal to 0.05555. This value is greater than 0.1612 value. We also know that MFA is equal to MFB. Finally, we are accepting the value that has been provided by SP16. That is, MFA is equal to MFB is equal to 5 by 96 WL square. So, span moment of the fixed beam is equal to MFS. We know MFS is equal to MS minus MFA. MFS is equal to minus WL square by 12 plus 5 WL square by 96 is equal to minus 3 WL square by 96. Finally, we have MFS is equal to minus WL square by 32. SF and BM diagram for fixed and beam with triangular load type 3. And this is our SF and BM diagram. Deflection at span of the fixed beam with triangular load type 3. Deflection pattern of the fixed beam for load type 3. This is the deflection pattern. Maximum deflection will occur at the center of the beam, which is also point of contraflexion for this type of beam. Say at a distance x, load is equal to 2WL into x. Reaction RA is equal to WL by 4. MF is equal to WL square by 24. We know that. Here, plus P1 equal to P. P is equal to x by 2 into 2WX by L into WX square by L. MP, that moment produced by P is equal to WX square by L into x by 3 into WX by is equal to W into x to the power 3 divided by 3L. And moment due to reaction RA is equal to RA MRX is equal to minus W into L by 4 into X. Next moment to X is equal to MFX is equal to MFA plus MP1 minus MRX. Where W square by 24 plus WLP by 3L minus WLX by 4. We also know differential equation for moment at any section MFX is equal to EI d2y dx. Therefore, EI d2y dx2 is equal to W square by 24 plus WX cube divided by 3L minus W into L into X divided by 4. This is our equation number 1. By integrating this equation, we have EI dy dx is equal to WX square into X divided by 24 plus X into 4 divided by 12L minus W into L into X square divided by 8 plus C1. We know this is the coefficient for integration. And when X is equal to 0, dy dx is equal to 0 and C1 is equal to 0. Therefore, the equation becomes EI dy dx is equal to WL square x by 24 plus W into x to the power 4 divided by 12 minus WL into x square divided by 8 is equal to. This is our equation number 2. Once again, by integrating this equation 2, we have y EI is equal to WL square x square by 48 plus wx to the power 5 divided by 6pl minus w into l into x cube divided by 24 plus c2. C2, once again, it is integration constant. When x is equal to 0, dy dx is equal to 0, then c is equal to cp is equal to 0. Therefore, y ei is equal to w l square into x square divided by 48 plus x plus w into x to the power 5 divided by 60l minus w into l x cube divided by 20. We know when x is equal to 0, when x is equal to l by 2, y will be maximum. By changing the value of x by l by 2, we have y ei is equal to w square by 48 into square by 4 plus w into 60l into l to the power 5 by 32 minus w into l by 24 into l cube by 8, or y ei is equal to w into l to the power 4 divided by 192 plus w to the power 4 divided by 1920 minus w to the power 4 divided by 192. So finally we have maximum deflection span for loop type C. Y max is equal to minus w to the power 4 divided by 1920 EI. Yes, negative side indicates that deflection is downward. Yes, you are the right person to me, whom I can request. Don't worry, I am not asking any money from you. Since you are watching this video till now, yes, you are the connoisseur of the structural design and analysis. I have a request to you. I am asking no organic watching hour from you. Only you have the veto power to add organic watch hour to my channel. You may think, how can you do this? You can do this by taking the following action. By providing more time in my channel, by sharing the link of my channel, by making regular comment and providing like, by any neighbor that you know, but I don't know. I can assure you that your investment will provide you dividend in near future. Now, how to collect your free Excel sheet? You can request for any Excel sheet that I have explained in my channel absolutely free of cost. To get any Excel sheet, you have to follow this. Not more than one sheet per month. First, you have to write in the comment section of YouTube name of the sheet on. About you, student or professional, from which country and place, then mail me. My email is Pranab Chatterjee, PRONAB, CHATTZ1 622 @gmail.com. After receiving the mail, send me the acknowledgement through YouTube comment section. After viewing, give me the feedback through YouTube comments only. After getting the file, instead of redistributing among the friends, share the link of my channel. Now, I'm switching over to Excel spreadsheet for the numerical calculation. Welcome to my Excel spreadsheet for the problem of UDL. Now we are changing the load type. Triangular load. First I am considering right hand side. Here the right hand support load is maximum and at left hand support it is 0. It is also a distributed load, distributed varying load. We have length of the beam 6 meter, width of the beam 250 mm, depth of the beam 500, clear cover 25. We can change this 25, 30, 35 as per our requirement. FCK, we can also change this 15, 20, 25, 30, etc. FY, the grade of steel, we can also change this. Main bar diameter 25 mm, stirrup bar diameter 8 mm, stirrup legs, we can also change this. Now, load. Here the maximum load on left hand support, right hand support 10 kilonewton per meter. Then shear force for simply supported beam, left hand support will be 10 kilonewton, and right hand support will be 20 kilonewton, and span moment will be minus 23.09 kilonewton. For fixed beam, maximum shear force left hand support 9 kilonewton, right hand support 21 kilonewton, and bending moment left hand support 12 kilonewton, right hand support 18 kilonewton, and span moment minus 7.630. Now when we are going to change the load pattern, that is when we are changing load pattern, maximum load at right hand support, left hand support, when maximum load is at right hand support, then all these values will interchange their position except span moment. Look here, now I am changing from right hand support to left hand support. Here on the left hand support the load is maximum and all the values just interchange their position except the maximum span moment and the deflection for the beam at span is equal to 0.229 minus, that is downward. Now I am changing position of the maximum load. Say the mid portion of the beam, the load is maximum, that is 10 kilonewton. And look here, shear force and moment for simply supported beam 15 kilonewton, left hand support shear force, and right hand support minus 15 kilonewton, span moment minus 30 kilonewton meter. For fixed end beam, shear force on left hand support 15, and right hand support also 15. Bending moment, left hand support 18.75, right hand support 18.75, and span moment 11.250. This is our data cell, and here all the calculation is there. Bending moment, shear force, simply supported beam, fixed beam, and total load, maximum support reaction, point of counterflexure, simply supported moment, fixed end beam. All the calculation I have got by the application of the formulas that I have explained in my PPT, PowerPoint presentation. You can check the result in your software and share your experience in the comment section of the YouTube. End of bending moment and shear force of the beam under different load and support condition in Excel, part 3. I hope you enjoyed it. forget to subscribe my channel. Thank you.